Thank you, sir. Mr. Surya Prakash is a highly accomplished civil engineer and entrepreneur. With a passion for his field, he has successfully handled a wide range of projects across India and abroad, employing a team of 100 engineers. He has been actively involved in professional organizations and held prestigious positions such as the past president of ACCE from 2013 to 2015 and the past president of the Pre-Engineering Structure Society of India. Additionally, he is founding trustee of the Smart Infrastructures Engineering Service Trustee since 2016. Throughout his career, Mr. Surya Prakash has successfully managed projects for the Ministry of Defense, public sector organizations and state governments. His areas of specialization include design, engineering project, management of buildings and infrastructure projects. Furthermore, he has served as an expert faculty for ESCI and CIRE in transmission line design and project management. I invite Engineer Surya Prakash to the upcoming session in order to gain an understanding of resilience in structural engineering. Welcome.
Thank you for giving a good introduction about me. And I thank Nebu Abram particularly for inviting me for this knowledge sharing session. And this is the topic I am talking for the first time. Though I have been working on last 20 years, it has given me an opportunity to document what I have done in the last 20 years in this resilience in structural engineering. So the overview is, I'll give base introduction and about resilience and about structural engineering, climate change and need for resilience in structures, and strategies and approach to resilient structural design, and finally the conclusion. This is in short. So we are all aware about built environment, how fast it is growing and growing population in the world and need for built environment and its sustainability. We are very well aware. At the same time, we are also seeing the climate change. These two are complementing each other. The population growth and need for built environment and climate change and need for more resilient built environment. And we are aware there are disasters and hazards growing. I'll be talking about it, and the structures to be resilient for resilient communities. Communities have to be resilient. We have had experience in the 2020 due to COVID-19, and we were resilient to respond to that disaster, and then we have rebuilt our societies and communities. Similar way, the structures also need to be resilient to the hazardous extreme loading conditions, which we don't estimate or which are not prescribed by the codal provisions. And we are aware of our east coast, like Orissa, Andhra Pradesh, Tamil Nadu, how they are prone to hazards and how we are resilient to those hazards, like cyclone hazards. And next, Netherlands is a country where we are affected by the storm surge and how they have built resilient infrastructure. Next, Japan is another example of resilient structures for earthquake resistance, how they have built the resilient structures. So we need to adopt these mitigation measures to tackle these hazards, unexpected loading or extreme loading. And we need to have the codal provisions and engineering practices and materials particularly, and methods of construction. These are all the things which I'll be touching today. So resilience is basically the capacity of the body to imbibe energy when the body deformed in its elastic state. And quickly to understand, so this is what we see in a ball. When it bounces back, there is a resilience in the ball to regain its shape, though it is affected due to the elasticity. And the community resilience we have seen after Mumbai terror attacks, and the buildings play a critical role, like Gujarat after the earthquake, or Kerala after the floods, and Andhra Pradesh after the cyclones. Like that, we are seeing the resilient communities post hazards. And importance of providing emergency response is very, very essential. And so the community resilience is very important. And for community resilience, built environment resilience is also equally important or even more important. So because of the significant economic costs and potential loss of life associated with this hazard, we need to have resilience in the infrastructure. So here you can see the ecological resilience. When you have a cyclone, how the trees respond, the natural structures, how they respond. There is a lot of resilience. And I'm sure you must be knowing that one of the ways of estimating the wind speed is the survival, survival of the trees and their age. If a 100-year tree cannot survive a cyclone, that means the cyclone's wind speed is higher than 100 years. So that's how we utilize this data. Next, the floods, how they affect the built environment, mainly covering action and the collapse of the buildings. Though structure is resilient, if the foundation is yielding or soil is yielding, it's not resilient. So we have to understand that. Next is the landslides. When there is a landslide, if we don't tackle the landslides basically, though the structure is resilient, it will not stay. And next is the best example of resilience in the world is the Leaning Tower of Pisa. Though it is not designed for such settlement, the tower has got the inbuilt resilience. That's why it is surviving even after the settlement beyond the design. So this is the example of resilience. And then we see earthquakes. Most of the buildings, though not designed, survive the earthquake because of the resilience in the building, because of the, you call it the redundancy or you call it the robustness in the structure. So this is the resilience. Next is the fire accidents. This is another thing which we don't design exactly the structures, but structures survive the resilience. I'm going to give the examples of practical projects which we handled with this, utilizing the resilience in the structures and restoring the structural life. Next is the man-made errors during construction or after the construction. So we see the structures failing. So even for man-made errors, we have resilience in the structures. I'll be tackling that example. And next is the cyclone, structures being not resilient. We see the failure. Terrorist attack. We have seen the World Trade Center. It has collapsed, but the resilience in the structure has helped saving many lives. You know, even after such attack, there are only deaths of 2,700, though the people in the building were more than 6,000. So many people could be saved, lives could be saved because of the resilience in the structure, though limited period. So now I'll get into the actual resilience. So we have different types of resilience. We have adaptive resilience. That is normally happens in the nature and human body. We have adaptive resilience, like what happened after the corona attack. We were resilient and we have adapted to that. Similarly, structures can have adaptive resilience, that is like self-healing kind of concrete that we are using. Next, engineering resilience. That's what is important for us. We engineer resilience for the structure. We have done the projects for giving resilience to the infrastructure, particularly in Andhra Pradesh. I have handled the project. And next is the ecological resilience. That we see in nature, ecological resilience. It takes time, but a tree that is damaged or a cyclone, it reconstructs itself over a period. That is ecological resilience. Finally, fails and no resilience. That we are not discussing today. So structural resilience is the ability to rapidly resume to use of the building, except for cosmetic repairs, like what happened in Gujarat. I was in Gujarat post-earthquake. I'll explain that, what we have done for giving resilience to the structures, for rebuilding the communities. And avoidance or diminution or removal of identified threats or hazards. This is the major part of mitigating the hazards and building resilience to the structures. And the preparation for disaster event scenarios. So what are the, like any project that we do in a given area, what are the possible hazards, possible threats for the structure, and we have to build the design basis for mitigating those hazards and giving the resilience to the structure. Now, if you see the design, it all started with intuitive design, we know, and then code-based design, that's normally what we do, and then we have performance-based design. That is actually, we estimate the hazard and we design for that hazard, that is a performance-based design. Next, consequence and risk-based design. This is also calculated. We calculate the risk and we design for that risk in the structure. Finally, now the latest that today we are talking about is resilience-based design. Means we cannot estimate the hazard, but we build the resilience to the structure. So even if you have the loads that are unanticipated, the structure should be safe enough to withstand such extreme loading conditions. So now let us look at the climate change that we are all aware. Now it is most talked about subject in the world actually, climate change. Global warming we know and its impact on temperature rise and excess rainfall which we are experiencing. I'll show the data, what I collected to show how the climate change is affecting, and then excess rainfall will cause flooding. We have 100 years flood data, but it will exceed the 100-year flood data, what happened in Kerala recently. So same in cities also it is happening. And the cyclones, we are seeing the cyclones with the wind speeds that are exceeding one after the other since last 20, 30 years. This is the effect of climate change. So this demands for the design, resilience-based design, because we cannot estimate what kind of wind speeds you will encounter, what kind of flooding you are going to encounter, and next temperatures, rising temperatures. Like now in Andhra Pradesh, it is recording highest temperatures in the last 100 years, 49 degrees in a coastal area. You can imagine. So what effects it will cause to fire accidents in the buildings. So nobody would have designed for the temperature change, the structures. But structure, if it is resilient, it will withstand that kind of temperature. So now this is the picture of Hyderabad in 2020 October due to the floods, which is never anticipated, which has exceeded the 100-year back flood, which was mitigated by Mokshagundam Visvesvaraya. So this is the rainfall data if you collect. So in 100 years, there were 5 peaks of rainfall in 100 years. In the last 20 years, that is 2000 to 2000 now, there are 6 peaks already. In 22 years, we have 6 peaks of rainfall, 100-year peak rainfall. So this itself tells us about the need for resilience. So resilience in structural engineering now is established, the need for resilience. That means we talking about 1.5 overload factor or partial safety factor and just saying that my structure is safe is not safe enough in future because the loads are exceeding. By the time we estimate the real loads, we will cross the hazard. So we examine the strategies and techniques used to design against these hazards and build in the resilience to the structure. And so we have to estimate the risk and we have to see how big they are. And when they fail, people may be killed. But no human activity is risk-free. So how safe is safe enough is the question actually in resilience. So we have worked on it, on arriving at the mitigation measures in various types of projects, whether it is earthquake or cyclone, fire and all, which I'll be talking today and sharing the. So today I'll be talking about floods, landslides, earthquakes, soil settlement, fire, man-made errors and pore water pressure due to flooding and cyclones and terrorist attacks. So this is the Gujarat earthquake and the examples that I'm going to talk about today is Gujarat earthquake and residential, 26-storied residential towers where we had the uplift of the raft itself and then Bangalore building stability after the soil failure, and power transmission towers, mitigation, and communication towers, IT park restoration after accident, and blast resistant structures. This also we can build in the resilience in the structures against blast. So what are the mitigation measures that we can handle? One is the materials. In the materials, we can go for fiber reinforcing and latticed concrete. Latticed concrete is the one which has a lot of resilience in the basic concrete itself. And then structural systems, we have to build in the robustness and redundancy. And design philosophy, limit state design we have with the partial safety factors and ductile detailing. That is, ductile detailing is the built-in resilience for earthquake resistance. Next, dynamic damping for wind resistance, and base isolation for seismic resistant design, and uncertainty modeling. This is the latest trend in the structural engineering. That means we can estimate the risk, we can estimate the probable load increase in the coming life of the structure, and then design for that overload factor. That is loads, estimated loads, change in the material properties, and change in the geometry of the structure. So this already is in the research stage, and very soon it is going to come into the codes in the coming 2 decades. So floods, we have material cover and protection, and then landslides, we have to do the ground improvement and reinforce the soils. Earthquakes, we have to do the structural model and then isolate the foundations, and damping we have to build in, and codal provisions we have to follow. Soil settlement, monitoring and timely restoration. Fire, man-made errors. I don't know what is the time available for me. Because it's a very important thing. Yeah, thank you. So man-made errors, we have engineering methods and enforcement. Pore water pressure, relief wells, we can give the relief wells for the pore water pressure. That's actually practical example I'll share how it helped us, relief well. And cyclones, mitigation measures, and terrorist attacks, security, surveillance, and then blast resistant structures. This is an example of fiber reinforced concrete, how resilient it can be. A bendable concrete. This is already there, available. So we can have a concrete, that means we have the resilience in concrete. Most of the projects, most of the structures fail because of the failure in compression. You know, we know ultimate failure of any structure is by buckling in concrete, in compression. So that is the thing, and if we can handle that, we can handle the failure. Next is the flood resistant material. Making a building flood resistant involves use of resilient materials. Again, the cover, and protecting the structural foundation against the cover. So these are all the important things. And some of the flood resistant materials include glazed brick, concrete blocks, and glass block, and stone with waterproof grouts, and then naturally decay material, resistant lumbers, and marine grade plywood and cement boards. These are all the materials that we can use against flood. Next, fire resistance. When we talk about fire resistance, it is the encased steel structure. Normally we use steel structures, but if we encase with concrete, the fire resistance will increase. And then we have the intumescent paint and vermiculite clay, which will increase the fire rating of the structure, whether it is concrete or steel. And board systems, we have the cement boards that we can cover the steel structures to increase the fire rating. Next is the structural systems. We have moment resting frames. That is a very primitive thing, which has, let us say, if we have 10% resilience in frames, in braced frame, we can get 20% resilience. Then, if we go for shear walls and core systems, we can increase the resilience to 50%. So that's what. So we have to choose the structural system depending on the resilience required. This is the resilience-based design. So now I'll go into the case studies. Hyderabad flood, we have done the study and we have prepared the mitigation plan for Hyderabad flood. And now you must be aware, Hyderabad is implementing strategic Nala development project. That means to mitigate the floods in future, they have implemented. So this is the study we did, identified all the lakes, their capacity. Lakes are being encroached everywhere. We are very well, so we cannot do anything about it. But what is the available lake now and how we can protect, and then which lakes have excess capacity compared to their catchment area and which have under capacity. So we connect these lakes through the nalas and then we mitigate the flood. So this is the plan we have prepared and submitted to the Greater Hyderabad Municipal Corporation. Next is the deep excavation soil collapse. We have taken all the measures like shoring for a 20-meter deep excavation adjacent to a building, but still we had a mitigation plan. If it collapses, what should be the mitigation? So that also we did. So we installed the structural health monitoring systems before excavation only. And it really helped us with the data when it collapsed, how much damage it has caused to the structure and is it safe to be reoccupied. So this kind of resilience, so this is the collapse of earth and still the building was safe and we had to convince the people to occupy the building immediately with this structural health monitoring. So that is the mitigation. So we have done the rescue and relief operation for the collapsed earth within 48 hours and reoccupied the building within 60 hours. So this is the mitigation and the resilience how we have utilized by monitoring. Next is the earthquake. So earthquake on January 26th, Gujarat, I was there on 30th January in Ahmedabad to assess the damage for the building and we drafted the damage assessment code along with Professor A. Surya. So these are all the structure condition, but still they have not collapsed. So there is a resilience in the structure. So we had to utilize that resilience and rebuild the structures without demolishing. And we had formulated the guideline for restoring and retrofitting the structure and given guidelines because it was a massive reconstruction in Gujarat wherein we have come up with a simple empirical formula to reduce the stiffness difference between stilt floors, open stilt floors and the infill walls. So that we have given and they could immediately restore those buildings and give the resilience to the structure. Now, if we have to design buildings afresh, any new building, now we have the latest technologies like base isolation and we have the different base isolation methods which will reduce the loading itself and then we have the damping systems. So this is the seismic mass dampers and we have the viscous dampers and we have the friction dampers, we have the yielding dampers. So these are all available different. I have come across in Japan a building being designed with 5 types of dampers and retrofitting the buildings, existing buildings. Same thing we can do in India also. And we are all aware Delhi is the highest risk seismic hazard now. So we have to take measures to do that. So next is the ductility detailing as per 13920 code. And if we strictly do that, we will build in the resilience automatically in the beams and columns, the column reinforcement and detailing. Next is an interesting resilience that I have done in a project of a water retaining structure. It's an aqueduct of 1.2 kilometers, wherein we had to do 2-stage casting of concrete. One is the base slab and then wall. So before casting of wall, there was a settlement of the soil and there was a crack in the slab. So then we had casted the wall in a W shape, wherein the crack got closed due to compression because once the wall is cast, the neutral axis comes down and slab will be in compression, so we didn't have to bother. So this is the kind of structural resilience that we have in structures and we can utilize that and rebuild the structures. Next is the fire. Very good example. Of course, I had many examples, but I will share this. This is reinforcement exposed in a flat slab, completely exposed reinforcement, and then drop panels also. You can see, but this structure was safe. You know, how we got resilience in this structure is because of the post-tensioning. We did the post-tensioning in the slab, and that saved the structure, and we could restore the structure to its original capacity by doing the shotcreting and rebuilding the structure. Next is the same PT slabs. During construction, we have a problem. Like, you know, when the building length increases, is more than 45 meters, you can't do two-side stressing also. So then we have to have a pore strip in the flat slabs. But this pore strip is a problem like when you don't provide counterprops for enough. Normally we provide counterprops for one floor, but here in this project we have to provide for 3 floors. We provided the counterprops for 3 floors, but you know, concreting happens in the night, 2 o'clock and 3 o'clock. And so the workers, we don't have control. They have removed the counterprops at one level. And then with the pore strip, the span of the slab has become 8 meters and it has cracked. So this is the cracks condition of that slab. So we had to restore. So this is the pore strip and these are the cracks after removal of the props, and we restored that structure by jacking up. This is again resilience in structures. We could utilize that resilience and then rebuild the structure, and I had a... here, sorry, I didn't explain. So here 2 levels of counterprops are there. So this removed counterprop has caused the damage. So this kind of resilience we can use, and we have restored the structure successfully. Next is the flooding, rise in pore water pressure. This is another example which we handled in practical case. So this is the damage in the podium columns. There are 2 towers of residential. In between there is a podium slab, and due to the flooding and pore water pressure rise, the whole podium got lifted. So this is the podium structure. Can you imagine this structure is being lifted by almost like 200 mm, 250 mm up due to the pore water pressure. So this is the representation of that lift actually. And we restored this just by providing a relief well and reconstructing the columns, the damaged columns restoring, and then the structure got restored. This is the water table study that we have done in the area, and we have provided the relief well, and then it worked successfully. Next is the cyclone. My experience in year 2000, we were given to study and provide hazard mitigation for AP cyclone for transmission network. So we have done the tower stability is mainly based on the performance of the legs, you know, the lattice towers. So this is the tower that has collapsed, and one size clearly does not fit all when it comes to this. So we have done the plinth level stub corrosion, strengthening of leg members, strengthening of bracing, strengthening of foundation. So this is the mitigation that we have done, and we have drafted the design criteria. In fact, can you change the slide? Next slide. So whatever recommendations we have given have become the part of IS 875 now 2016. The narrow front wind and coastal wind zone. Now IS 875 has incorporated coastal wind zone. So the structures that we design in coastal areas require separate design criteria. And these are all the strengthening measures we have done. And this is the strengthening of the bracing in the towers. Foundation is unhealthy base. It is better to do the strengthening. This is the foundation failures which we have restored by doing the filling of the soil. upgradation is the process of increasing the capacity. So we have done the upgradation of the transmission lines also by increasing the peak height. So review the design criteria and construction practices, coastal zone, narrow front wind and survival speed, minimum depth of foundation and plinth height we have revised, retrofit existing critical infrastructure for community resilience, prepare hazard mitigation plan periodically. This is our recommendation. Adopt from other similar zones. Like we know that this climate change will affect the wind speeds and flooding. We have to keep changing that basis and make pre-monsoon inspection of structures mandatory. You know, we have seismic qualification of the structures to be done once in every 5 years. That is a mitigation measure for seismic resistance. Same way for cyclones also, we have to do the pre-monsoon inspection. Strict adherence to CVC norms, Central Vigilance Commission in quality. So these are our recommendations. Finally, the terrorist attack. And one more important thing I want to suggest for the cyclone. For example, we have the spun concrete poles, which we use for distribution network. We have pre-stressed concrete I-section poles. We have steel I-section poles. So if you see the resilience, I-section pole is the least actually. Next comes the pre-stressed concrete. Next comes the spun concrete poles. So we have recommended use of spun concrete poles for all the distribution networks in cyclone-prone area because of their resilience to torsion actually. So this is the very important point. Next is the terrorist attack. We are aware that World Trade Center fire rating saved many lives. Fire rating saved many lives. But still structural system did not save. So that is why we have to have blast resistant structures and we have to use base isolation against this one, robustness and redundant structural systems and the redundancy in infrastructure. Then emergency restoration and latticed concrete. In fact, we have designed some of the blast resistant structures for defense, which I cannot name because of the confidentiality, but we have done the buildings 60 meters below ground, which are resilient to nuclear attack. So we have a design like 15G acceleration due to nuclear attack. Normally, our highest earthquake ground acceleration is 0.4 G. Whereas with the nuclear attack, the ground acceleration can go to 15 G. And that we had to damp to 0.6 G. So this is actually part of my analysis where by using the damping systems and by using the isolation, we could do the damping in blast resistant and build the blast resistance to the structure. That is the resilience we build. So finally, the conclusion for my topic today is engineering the structure with the proper risk and hazard assessment should be made mandatory. Risk assessment should be made mandatory and drafting proper design basis for resilient structures with the recommendations that I have given for materials and the structural system and uncertainty modeling for materials, loads and geometry and robustness and redundancy in structural system should be, we do the robust analysis, particularly for precast building. We have to do the robust analysis. Steel buildings also, we have to do the robust analysis. Same way, when we have to build resilient structures for hazard, we have to make it mandatory to do the robustness analysis. Thorough investigation for all aspects like flooding, pore water pressure and wind speeds, all that has to be done. And selection of materials and right code provisions. And finally, resilience in structures in disaster-prone areas shall be part of design basis and not an option. So this is my recommendation, and I thank organizers for giving me this opportunity.
Thank you, sir, for sharing your valuable knowledge on architectural engineering, understanding the concept of structural resilience, the impact of climate change and natural disasters in today's design and so on. I now invite Mr. P.A. Salahuddin, Chairman, Institute of Engineering India, Cochin Center, and Mr. Nebu Abraham to present the memento to Engineer Surya Prakash.
Sorry, there is an announcement. Actually, we were planning to have a panel discussion now, but unfortunately, our key panelist, Mr. Jitin Shah from College, he has had to return to his base on an urgent commitment. He had a message from home and we had to rush back. So therefore, we are forced to cancel the panel discussion scheduled for now. So we shall be meeting again tomorrow morning at 10:30 to listen to Ankur Modi speaking on innovations in urban design, building in the cities of tomorrow, and also Padma Vibhushan Sridharan sir giving us the first annual CP lecture. So we expect all of you here by 10:50 tomorrow morning. Thank you very much. Thanks for your active participation. Thank you. Oh, yeah. There is tea for you. There is tea outside, tea waiting for you.